Okay, so we set up the null hypothesis of the Bruce-Godfrey LM test. So we want to see whether there's any correlation with residuals. So in order to measure the correlation, and in order to be able to test this, we need to be able to work out, we need to be able to estimate the shock epsilon t. So first things first, we have to approximate this. So we use the fact that under the null hypothesis, the OLS estimates of these true coefficients will be consistent, which means that for t large enough, the estimates will be near to the true values. So if we take the estimate of the residuals, then these should be near to the true residuals when t is large. So this is what I was saying before it cut off. Okay, so we can estimate epsilon t by taking yt minus the fitted value. And all we do is, well, we plug in yt, and we have the fitted value here. Take one from the other. So when we take this from here, we're going to be left with what we want, epsilon t, plus these two terms here. And what do we know about these terms? Well, for the sample size big enough, both of these will be near to naught. So as t gets bigger and bigger, we know that mu hat tends to mu, and phi hat 1 tends to phi 1 in probability. So that just means that epsilon hat t, this is very hand wavy, but this essentially means that our estimate of the residual gets near to the true residual. So in essence, our estimate will be approximately near to what we want, which will be especially when t is large. So then we can test whether there's zero correlation in the true residuals by seeing whether there's any correlation in the estimated residuals. So is everything still okay? We've only got 3 people back, I think. Okay, so I'll just assume everyone can see okay. So that's why so the first step of the test, run OLS, estimate the parameters, then estimate epsilon hat t. Then the next steps will then be, in essence, to test whether we observe any correlation in these estimated residuals. So the next step of the Bruce-Godfrey LM test is to set up what's known as an auxiliary regression. We regress epsilon hat t on a constant, and again the coefficient names here are arbitrary, a constant plus, say, alpha 1 yt minus 1. So we regress it on a constant and the lag of y, so we're doing it for the AR1 here. So we include as regressors a constant and lag of y as in our model, and then we have plus, call it say xi1 epsilon hat t minus 1 plus, call this say eta t. So again, the coefficient names are arbitrary. So there's no real intuition to this regression aside from the fact that under the null hypothesis, under H0, that there is no zero correlation. What Bruce-Godfrey showed is that the sample size times by the R squared from this regression will get nearer and nearer and nearer to a chi-squared distribution. Sorry. We include it up to lag k. Will tend towards a chi-squared k. So again, we specify the test where we include k lags. So the Bruce-Godfrey LM test, the auxiliary regression, you regress the estimated residual on all of the included variables in our model. In our case, we've just done an AR1. But if we had an ARP, it would include all the way back to yt minus p. Then we include all the lags of our estimated shocks up to the specified level of the test, k here. What we can show is, this is called an auxiliary regression here. So again, you can't just look at this and see it straight. It's not intuitive necessarily why this holds. And again, you don't need to prove this. You just need to know if we run this regression and we calculate the R squared, which is all done in e-views. If we multiply it by t, then as the sample size gets bigger, then the distribution of t times r squared gets nearer and nearer and nearer to the distribution of a chi-squared k. So we can use this then to perform a test. If our test statistic, t times the r squared from that model, is too big, i.e. bigger than the critical value of a chi-squared k, then we reject. So for example, the chi-squared 1 distribution looks something like this, say, and so on. So if you want to do a 95% test, what the critical value maybe say 3.1, and there'll be 5% in here. So if t times r, so if our test statistic t r hat squared is greater than the critical value, we reject. Otherwise, we accept. And again, the critical value is found by for example, if it's a chi-squared 1, we find the value which gives us 5% to the right. And this test is done automatically in eViews. Okay, so when you saw the Bruce-Godfrey LM test, it gave you the test statistic and it calculated the p-value. So the p-value would just be the probability that our test statistic is that it's a probability that a chi-squared k would be bigger than our test statistic. Okay, so it's the exact same idea of any test. This is the crucial result, that when we run this regression, t times the r squared is approximately chi-squared k. So we get the critical value from the chi-squared tables, or it will be done automatically in eViews, and we can perform the test. And again, the p-value is a probability that the null is true. Okay, so does everyone follow this so far on the idea? And again, you just need to be able to outline the steps. And it's helpful if you understand the intuition of why we get the result. Okay, so again, it just turns out that this regression, it's selected purely artificially because t times r squared behaves like this under the null hypothesis. Okay, so there's no other reason why this works. Okay, so that's it. That's the 2 steps to the... And again, for an exam type question, you'd be expected to state how we do the test. So again, we get the test statistic. If it's bigger than the critical value, we find some evidence to reject. Otherwise, we accept at whatever size test we do. Okay. And we also saw in eViews that there were 2 tests. There were 2 columns, 2 rows, and they both did the exact same test. They just used different test statistics. So this is one way of doing it, the Bruce-Godfrey test. Another way, I think more intuitive, if we want to test. So we're highlighting all this through an we're highlighting everything holds exactly the same for an ARP. Again, plus epsilon t. We want to test that the errors are an AR1, an ARK, say, plus theta k, where VT is white noise sigma squared. So this again, and we want to test, and again the coefficient names don't matter here, we want to test that theta, all these coefficients are not, against the alternative that one of them doesn't equal not. So I'm just reiterating the test again. So again, with another way of doing this test, I think more intuitive, another way to test this, that the errors are correlated, is again, first run OLS, estimate the parameters, take the fitted value and estimate the residuals. And again, give all the details of the steps, where y hat t is the fitted value. Then we can just run this regression and do an f-test. So we can regress epsilon hat t on, well, theta 1, epsilon hat t minus 1. Plus, and again, we'd have some error. And we just do a test. We just do an f-test. So we can just do a joint test. This is just a regression. We regress the estimated shock at t on k lags. This is just an AR regression now in the shocks, and again we can test that all these coefficients are not. Again, one of them not equal not. So this is an alternative test. I think this one's more intuitive than the LM test. we can see, again, we want to see whether the errors are in ARK, where we specify the lag k, 5 or 10 or so on. We run OLS, estimate the residuals. We then see whether there's any correlation in the residuals. So we just run an ARK in the errors, the estimated shocks, and then do an F-test that all the slope coefficients are not. So this would have been, if you're looking, when we come to see E-views, you'll see two rows. One does an F-test and one does a chi-squared test. The chi-squared test does the Bruce-Godfrey test, and the F-test does this test here. And they almost always give the exact same answer, because they're doing the exact same thing. I think this F-test makes more sense. You can see very clearly how running this regression and doing an F-test directly tests the null. Whereas for the Bruce-Godfrey LM test, this regression here is not really, there's no intuition here, it's just very mechanical. It just turns out that t times r squared from this regression will be a chi-squared if there's no correlation. Okay, so I think testing serial correlation is relatively intuitive, and again, you don't need to prove any result. So are there any questions on this? Does everyone follow the intuition of testing for serial correlation? And everyone's clear on why, and again, just to make clear, we can do this test for an ARP. So we can, for an ARP, we'll estimate all the coefficients, take the fitted value, do the exact same test. The same for an ARMA model and so on. Okay, so for whatever the model is, an ARMA 5, 10 and so on, estimate all the coefficients, take the fitted value, estimate the residual, and then test whether there's any correlation in the residuals by running either one of these regressions. Okay. So are there any other questions on testing for correlation? And does everyone understand why correlation causes a bias in these AR models? So we saw two problems of when we have, let's again take the case where yt equals, we saw two problems, we highlighted two problems in the lectures of correlated errors. One of them is that if the errors are correlated with the past, then epsilon t is correlated with yt minus 1, and therefore OLS will be biased. But a bigger problem is if epsilon t is correlated, then it means that our specified model doesn't capture all the dynamics. Okay, so then what this would mean is, to take an example, suppose that the errors were an AR1. Where VT is white noise. This then means if theta 1 doesn't equal naught, then the errors are correlated. Okay, so these are just, again, this is just now relatively basic algebra. If I asked you now to write yt as a function of past values of y and vt, then, well, we just plug epsilon t into here. So we know from here that epsilon t is yt minus mu minus this. So just rearrange. And again, we can lag back one period. So everything holds equivalently one period back. So that's it. So you just plug these two into this equation and rearrange. So you're literally just rearranging equations here. This allows us to write yt as a function now of past values of y, things that we can measure, and a white noise shock. So what we're doing here is, this just, if we run this regression, the errors are correlated, it essentially means we've missed something out. There's some dynamics that we're not measuring. So we can now find out what the true model will look like of y if these two hold. So plug this in, so plug this into the left hand side, and we get yt minus mu minus, this is epsilon t, equals theta 1, and then epsilon, plug in epsilon t minus 1. Yt minus 1 minus mu minus plus, and then plus vt. And then just rearrange, so that's it. So we can just take, we want to get yt on the left. So we take mu and phi1 yt minus 1 to the right hand side. Then we're going to get plus theta 1 yt minus 1 minus theta 1 mu minus, and so on, theta 1 phi 1. So all we're doing is rearrange two equations, and then that's it. We can then simplify. This is equal to mu 1 minus theta 1 plus, then we're going to get theta 1 phi 1 minus plus vt. So we're just rearranging. So we have the true model is yt equals a constant, and we now have yt minus 1 and yt minus 2. So we have that the true model yt is an AR2. Yt equal, call it alpha plus phi 1, where, well, alpha just equals this coefficient here, phi 1 is this coefficient here, and phi 2 is minus this. So all we've done here is shown if we have an AR1 model, where errors are an AR1, well, you just use this equation, plug in the shocks from both time periods and rearrange, and what we've shown is the true y is an AR2. For some coefficients, alpha, phi 1, phi 2, given above, we have this Vt is white noise. So this is the definition of an AR2 process. So what we've just shown is that if an AR1 model where the errors are an AR1, it means the true model is an AR2. So in essence, we can think, another way of thinking about serial correlation in these models, in AR models, is essentially that we've got an omitted variable problem. What it means here is, in this model, in our model, we've omitted yt minus 2. Once you control for yt minus 2, then the errors, what's left is just white noise. Okay, so do you see what I was saying in lecture is when we have serially correlated errors, it's a much deeper problem than just a bias of OLS. It means we've not specified the correct model, and we've missed some of the, and so we can think of it equivalently as an omitted variable problem. So did everyone follow that? The idea in that case, because then we can generalize that then to any model, where we have any model. We could have, say, an ARP where the errors are an ARM and so on. So any questions on this so far? So what do you think is going to happen if we have an AR1 where the errors are now an AR2? So what do you think the true model will be? Just thinking intuitively from before, what do we think is going to happen here? Well, if you had to guess, like, what do you think the true form of the process would be if we had an AR1 where the errors were an MA2? The true model YT would be what? What kind of form would it be? Is it still coming through all right? Hello? Yeah, so the true model will be an AR3. Okay, so again, it will go on like this, and you can see that you can do this yourself. Now plug in epsilon t minus 2. We know that epsilon t minus 2 is a function of, well, it's going to be yt minus 2 minus mu minus phi 1 yt minus 3. So when we plug this into here, we're going to get yt minus 3 appearing, and so on. So if we have an AR1, if we have an AR1 So did everyone follow that? Does everyone see the intuition of why if we have an AR1 where the errors are an AR2? Again, I'm not going to go. You can work through this yourself. Okay, we can see intuitively when we plug in epsilon t minus 2, it's a function of yt minus 3. So we're going to have we're going to have an AR3 model, and so on. So we're just seeing then if we have an AR1 with AR say m errors, where m could be anything, it implies a true model. True model is an AR m plus 1. And this all generalizes. If we have an AR, say, 2 model, plus epsilon t, then if the errors were, say, an AR1, then we'd have what kind of model with a true model? So if we have an MA2, an AR2 where the errors are an AR1, then what's going to happen here? So we run an AR2, but the errors are an AR1. So by a similar idea, we can work out epsilon t and plug it into here and into here. So again, you should be able to see we're going to get an AR3 because epsilon t is yt minus mu. And epsilon t minus 1 is going to be a function right back to epsilon t minus 3. So you should be able to see when you plug these two into here and rearrange, we're going to get yt minus 3 appearing, which will mean that yt must be an AR3 model, and so on. So the general rule is, if we have an ARP, if we have an ARP, so what we're just showing there, what we can see there is, and again work through this yourself, if we have an AR2 model with AR1 errors, then we can show that the true model must be an AR3. And this all generalizes. So if we have an ARP model with ARM errors, then the true model is an ARP plus M. So if we have, if we have an ARP with ARM errors, it implies the true yt is an ARP plus M. Okay? And again, so we could look at what happens when we have an ARMA 1-1 with AR1 errors, and we could look at what happens and so on. So for example, if we could have that yt equals mu, so we could have an AR1. And again with these things, it's just useful to play around yourself, and epsilon t. So what would happen if the errors were and what if the errors were not an AR1, but what if they were a MA1? So let's say we have theta 1 where VT is white noise.